Hi, class. Welcome back to campus for fall 2020. My name's Al Macker. I'm going to bring up our syllabus and then we'll get started with our semester. So, like I said, I'm Al Macker. This is finishing up my 6th year here at Marist teaching. I have my bachelor's degree in computer science from St. John's University. I have my master's in computer science and information technology from here at Marist. And like I said, I've been teaching here at Marist for 6 years. This is my first time teaching data communications to undergrads. Previously, I've taught it for 2 or 3 semesters to graduate students. I'm from Marlboro, which is just across the river from campus. Married, have 2 kids. One's a senior in high school and one's a freshman in high school. As you know, our class is online. We're going to bring up our iLearn site after we introduce our syllabus. I don't have an office on campus, so the best way to reach me is by cell phone or email. If you want to talk on the phone, please text me first and let me know who you are. And more than likely, we'll set up a Zoom or WebEx meeting and discuss things one-on-one. Our text is Business Data Networks and Security, the 11th edition. There's e-versions of it available as well as used versions. It will look like this. I recommend you purchasing and keeping the book. It is very useful. I also sent instructions on how to order LabSIMS Network Pro. That will be your lab part of the course, and it will be the foundation for most of the homework we have through the semester. This is just a description of the course. Data communications has grown in importance from when I got my master's in 2014. Excuse me a second. Sorry. I, in fact, took data communications twice while at Marist. The first time, I think it was in 1999. And then I didn't continue with the degree. And then when I came back in 2002, I had to retake it because things had changed so much in that brief amount of time. But we're going to be looking at different network types, different media types, different models. We're going to look in detail the OSI model, the TCP/IP model. Not that you're going to use this stuff in your careers, it'll just give you a foundation of how packets move from point to point, what a packet's made of. We'll look at routers, switching, Ethernet switching. We'll look at the client-server model for computing throughout the semester. So we have 11 chapters in class. We may do the 2 online modules. We'll see how we're doing. Our midterm is not cumulative. It's chapters 1 through 5. The final is chapters 6 through 11. I recently changed this a bit, and you'll see when I look at iLearn. Our midterm and final are worth half the class. Now they're worth 40%, sorry. Participation's worth 10%. Collaboration, quizzes, and test out make up the rest. And I'll edit that right after we start talking today. Our grade distribution, we already introduced LabSim. We're going to have short quizzes each week. That really shows me that you're reading the text and watching the videos. In addition, each recorded lecture, there'll be 1 per week. Some weeks I may put up 2 based on my schedule. And I am having surgery next week, but I expect to be able to record next week. There'll be an embedded question from our textbook that you'll have to answer as well. And there'll be placeholders for both within iLearn. We're going to have a collaboration project. And it's really to take everything we learned through the semester and build an organization's new office, building, campus, etc. There's some scenarios I gave: a single office with APCs for medical field. We can even move that into using mobile devices, using laptops, things like that. We can have a private college LAN with 8 buildings, like a campus area network. We could set up a WAN for a wide area network for a company in the US or an international finances company with offices across the world. We need a company background. This is a fictitious company, so you're going to make it up, or you can use a real one. You'll do a company needs assessment, which means what do they need? What's their office space look like? How do we get there? We're going to do an equipment list. You're going to do a pricing list based on just retail pricing you find online for the things you need, like routers, switches, cabling, etc. We'll need a logical network diagram. It says using Visio, but anything you can find freeware that can make network diagrams, just save it as a PDF so I can open it. We're going to see what we may need from network security. And we're going to see documentation on why you chose the equipment you did, needs analysis, maybe and finally, implementation plan. You're expected to watch the videos each week and answer the embedded questions, as well as keep up to date with your lab sim. I can have some flexibility with the lab sim stuff, but like I said, I would like it done each week. The semester schedule is right here. It is something that can change. It's fluid. Like for this week, we're supposed to do chapter 1, core networking concepts. We're going to have that done, and you're supposed to do lab 0, which is an introduction, and lab 1. The labs chosen here correspond to what we're doing in class. So you see, when we do chapter 4, network security, lab sim is actually module 13. Okay, I expect all work to be your own or the work of your team. In teams, I expect equal participation. If I get any notification from team members that you're not working equally, I'm going to have to intervene, and that'll look down when it comes to final grading. And with collaboration worth what it is, that could be a concern. So let me just take a quick look at Gradebook. Sorry for the delay. So yeah, collaboration's 20, exams are 40, test outs 15, quizzes are 15, and participation's 10. So I'm going to change that right now. The collaboration's 20. Participation's 10. Okay. So we got 40% for exams, 30% for test out and quizzes, for 70%, collaborations 20%, and your participation's 10%. So I'm going to stop sharing this. And I'm going to bring up our iLearn environment. In just 1 second, I need to change the tool order, and then I will bring that up for you. Sorry for the long delay. And here's our iLearn environment. Gradebook is at the top, followed by messages. I said the best way to get me is just message me through here. Our roster. There's WebEx for students if you want to use it to collaborate. I'm using Zoom to record this. There will be some forums throughout the semester. Our resources are where we're going to find our PowerPoints. Right now, other than chapter 1, they're just whatever the author puts out there for teachers. I've edited chapter 1 to provide some more clarity on what's being talked about. Our syllabus is here as well. I don't use the attendance feature in here because I will grade you on whether you return your lecture notes to me or not. So we see lecture 1. So placeholder to show we watched our lectures. It's going to be due on the 31st. I'll give you till Tuesday early morning to get it to me. And it goes right into participation and post. And now our first assignment's up. Oops, because I didn't do points. And I'm going to give a due date for LabSim 0 and 1. So LabSim will score your work for you, and I'll take an average of all the work you've completed, and that'll be the grade you're given for that particular assignment. And it will have an accept to date until the 1st as well. We'll give you to the end of the day, the 1st. I would like it on time, but I won't penalize you if you get it to me by the accept to date. Okay, so now you know your first 2 assignments. You've seen our syllabus. You've seen iLearn. Let's stop sharing this and get right into our PowerPoint. So we're going to be looking at core network concepts and terminology. We're going to discuss how the internet is changing, particularly in the means of security, how the internet's not a very kind place. It's great that everyone can access it, but bad people can access it as easily as good people. We'll look at some terminology and define who connects to the internet, who gives us internet access, and what the devices that provide us our pages back are. We'll look at some basic concepts and look at some flows for single networks. We're going to introduce things like core routers, access points, some things that you may be knowing of now, but we'll get a greater understanding throughout the next 15 or 16 weeks. So first, our chapter really always gives us some kind of case to begin with, and then it breaks it down in different pieces. First chapter is about 35 pages long. There's roughly 60 slides here. A lot of the slides are really showing flows that the book does a great job explaining to you. So the first case is a distributed denial of service attack on krebsonsecurity.com. It's happened 5 or 6, 10 years ago now, probably, where our criminal, the bot master in this case, decided to attack Krebs on security. And he did so by creating malware that got distributed on a bunch of Internet of Things devices. It got put on corporate networks and it got put on security cameras as the picture depicts. And once the malware was installed, we probably used a phishing attack to prey on humans' weakness to trust what they get in their email. So the botmaster probably sent an email out saying, hey, you want a free vacation, click this link. And people clicked the link and it got installed on their devices. Their devices now became under the control of the botmaster. The botmaster then flooded Krebs on security with so much network traffic packets that it couldn't keep up, and Krebs on security went down. I had one denial of service attack in my career. It shut down my company at the time, XL Capital Assurance, for 2 days to be able to clear up damages resulting from the attack. So this slide is just showing the botmaster issuing the commands, the bots acknowledging them, flooding the router of Krebs on security. So I did mention router. Router is just a device that connects to networks. It's really what's accepting all the incoming requests for data from Krebs on security. And Krebs on eventually got back to life. A more famous attack was the attack in 2016 on Dyn, maybe 2017. Dyn is a company, I use it at Greystone Programs. Remember my full-time job as IT director, and they're a company that hosts DNS, which we'll look at today, I believe, and it's domain name service. It's what takes IP addresses and turns it into host names. IP addresses, though pretty easy to remember based on where they come from, they're not so easy to remember based compared to KrebsOnSecurity.com. So about the internet. Our friendly internet started out as a military device to combat Russia during the Cold War. The US would use it to send secure communications from point to point. However, the military and US government got tired of it in the mid-90s as the Cold War was ending and it went public. And now it's managed by thousands upon thousands of internet service providers who are allocated a certain number of internet addresses, IP addresses that they can distribute to customers. So we see some terms here. We see host A, B, and C, and D. Hosts are anyone that connects to the internet. We see host A connects to Hawaii.edu's network. Now, Hawaii.edu is a URL depicting a DNS address. Hawaii.edu equals some IP address. So host A is on Hawaii.edu's network, B is on Microsoft's network, and C is on Panko's network, and D is just a smartphone connected, maybe through the air, LTE, 5G, directly to, say, AT&T. Like I said, 95, the US government turned the internet over to ISPs. That's when the dot-com era really started. And 4 years after that, the dot-com bubble burst. I was a casualty of that, and it was a great thing because I got a job that right after I worked for a dot-com that lasted almost 13 years until I got hurt. So that's where e-commerce really came about. And the survivors of that, Google, Amazon, are all thriving today. Those that didn't survive, it's a shame because there's a lot of good ideas out there. And today we have even more applications out there. We have social media, we have artificial intelligence, we have what artificial intelligence backs, like weather forecasting, like fantasy football help assistance, like helping doctors treat patients with cancer, like helping And what we're doing today, collaborative software. I'm using Zoom to record this. Slow internet back 5 years ago, 6 years ago, made it very difficult to video conference point to point. We typically had to use very slow speed dedicated phone lines called ISDN that were connected to devices called codecs that were connected to a video conferencing system that had big freestanding cameras, and you had to have rooms dedicated. Now I'm recording this in my basement and you're watching it on your laptops or smartphones. Times have changed. As I said, speed enables all of this. It lets us stream Netflix in 4K. It enables things like OneDrive and Dropbox to have large data transfers. Makes it very easy for us to back up our computers and our phones. Here at Marist, each of our Marist IDs come with a terabyte free of OneDrive storage from Microsoft with our Office 365 environment. That's a very powerful thing to get that much storage space for free. At Greystone and many other companies like me, we utilize the cloud to host our servers. Greystone, we have one physical, bare bones, bare metal server available to us with 5 virtual servers built on it. We rent that one box as well as memory, storage space, and processors, and cut our costs probably by 80% if we had to have 5 physical servers. Like I said, the internet's pretty much in reach for everyone, but it comes with a cost. Okay, we can now talk to whomever we want. Our human involvement is less. Look at what's going on in COVID. We're all working remotely. We're taking school remotely. My kids are taking online school now as internet decided to, not internet, Marlboro decided to not open right back up. So their involvement with other kids is suffering a bit. We now have what's called Internet of Things. The Dr. Pankos say Internet of Everything, and I agree with that. Internet of Things means any device typically not needing to be on the internet now is. We can see refrigerators that can tell us when we're running out of milk. My thermostats can tell me if it's too hot in my rooms and I need to throw on my air conditioning. My oil tank sensor can tell me when I have 10% oil left. I can set lighting based on when I'm home and not home. I can put sensors in my bathrooms that detect water leaks. I can have cars that can drive themselves. But keynote here, the first Internet of Thing device was the ATM. All those years ago. You guys don't even know of a time without an ATM. So I do. So now we're going to have a brief break to tell you one of our questions for showing you watch this video is question 9 in our text on page 10, the test your understanding. Why is the internet often depicted as a cloud? Why is the internet not about sending messages between hosts? So just a quick blurb on that, and then we'll have one more question towards the end of the chapter. So who owns the internet? Really nobody. The ISPs do collectively. So each ISP has the authority to give out internet addresses. You pay the ISP money, they give you an IP address in a certain speed. They manage your domain name service, your MX records. MX records are how the mail is routed. But that's mostly for corporations. Yes, they'll give us a DNS. They'll give us IP addresses. They'll give us DHCP, which is domain host control protocol, how we get our IP address automatically. All these funds come together, and that's how the internet stays the way it is. No one controls the internet either. That's why there's so much, computer crime. But there is an internet engineering task force um, that has standards, but there's no one setting any boundaries whether to say it's legit or not. Countries have regulations, like here in the US with the FCC, but it's not really that stringent. You go to somewhere like China, where they're very restrictive, they probably do a better job of managing the internet and crime within their country, but they're the second biggest computer crime country out there compared to the US. We talked about the internet being anytime, anywhere, but that's for good and bad people. So security is a big key. When the author made these slides 2 years ago, it was given that 10 hours a week was spent on security. It's more like 17 these days. Marist now has an IT concentration in security, as you all know. And it's really the best avenue to launch a career right out of college because it'll be the most exciting and the highest paying. Typically, you guys leaving Marist would be maybe junior developers or junior network admins or help desk people. And now you're security analysts doing a important, fun job, making some more dollars. So like I said, a host is anything connected to the internet. Here we see a browser application, a host connected to it, the internet depicted as a cloud. Depicted as a cloud really for two reasons. IT professionals draw it that way to do that everything everywhere, but more importantly, the internet shown as a cloud to emphasize that we do not look inside it at this point, it just works. It's giving you a look up in the sky, you wonder how the clouds are there, but you never really know. So the internet's purpose is to deliver messages from one host to another. This is the client server model of applications and application delivery. So here we see host A using Chrome sends a message to the internet like, I want to go to ilearn.marist.edu. So that request goes to the internet, DNS takes the host name, changes it to an IP address, routes the IP address appropriately through whatever route it has to take between routers, and it gets to marist.edu. So the web server then says, hey, you need to go to iLearn. Whoops, you need to authenticate with Duo Security. So you get a message back to ask for a push or a code through Duo. You do so. The acknowledgement of that code is sent back to the server, and then you're able to get to the web page. Like I said, clients are usually devices, can be servers. Here we have Apple desktop, we have some kind of smart watch, we have looks like a Lenovo laptop, we have Echo device, we have a touch screen, probably all in one like we have in the lecterns and Marist. We have a tablet and we have an iPhone. I don't know if any of you have seen a data center, but data centers have hundreds of things called racks. The racks are what's depicted here. That's these large rectangular black entities. Located in here, what the gentleman's holding is a rack server. This one in particular is 19 inches wide, and it can be as small as 1.75 inches. Each series of holes where on either side where the rack server gets connected to are called U's. That's 1.75 inches. Each rack can hold a bunch of these, but we're also going to have UPSs in here. We're going to have air conditioning in here. We're going to have routers in here. We're going to have core switches in here. If this was a smaller room, we would just have a regular Ethernet switch we have down here, and we have a router right above it on the left-hand side of the picture. My depiction of what Island was really takes care of this web service client server application. So our client puts in a request. It goes through HTTP, Hypertext Transfer Protocol. That's the protocol that takes our packet, organizes it, breaks it apart, sends it along its route, puts it back together, sends the acknowledgement and the resultant output. So ilearn.marist.edu goes to marist.edu. You ultimately get okay to log in, you log in, and you have our class site. Just realize though, not all requests for data come from a web server. They can come from a regular server. Communication is not always HTTP. Here you see a host using Excel to connect to a database management server using an ODBC connection to be able to pull data from the database management server. This model is pretty much gone, however, with the availability of high-speed database management servers like SQL Server being cloud-enabled and virtualized. We don't really see ODBC connections that much in the business world. So this really shows how a app message is created. Again, are you going to say, Al, 15 years from now, am I going to tell someone this? No, but it's good to know. So our steps are network application software creates our application message. Our transport process and internet process, that's HTTP, adds a TCP segment and header and puts the segment into a packet. And then our device is able to send the IP packet to the internet. So we don't ever see this, but ultimately it's this tablet sending a piece of mail out. And that piece of mail is made up of a bunch of segments that are put into a packet. And that packet looks like this. It has the application message with a TCP header attached to it. And we'll look at more about transmission control protocol later this semester. When we finally deliver the packet, we have an IP header, so the destination knows where the address, where the request came from, and how to route it back. The long application message is pretty much the same process as the short application message, but we put in the fragments to have quicker return on acknowledgement and ultimately final output. We're going to look inside the internet for a little bit. So like I said, the internet's a collection of routers connected via ISPs. So between host 1, 2, 3, 4, we have a bunch of routers to get to host 5, 6, 7, 8. And our goal here is to get our packet to 5, 6, 7, 8. So the packet is depicted as this envelope. So we have a routing table within our router A that says we need to go the shortest amount of hops to get to host 5, 6, 7, 8. So our packet leaves our host, goes over our fiber optic network to router A. Router A says, now what do I have to do? Well, I need to get it to the next router in order to get to 5, 6, 7, 8. So we have a route in place that tells us to go to route B. It could go to any of the 6 routers in the US and South America on the diagram, or it could go to the 2 routers in Canada, but it chooses to go from, looks like Portland to New York to London, to India, to could be Russia, down to Australia, and finally that's where our host is. Okay? All done through a routing table. And here's a picture of a rack router. It says see a trend here. It means most of our equipment is stored in one place. They're all co-located together within a rack or many racks. We connect routers to switches via fiber optics. We connect routers to ISP through fiber optic. There's two types of IP addresses. I'm sure you all know about IPv4 addresses, the 10.10.10.1 address. And that's what our routers are delivering. So each IP address is unique across the internet. You can't have duplicates. They're 32 bits long. Bit is made up of ones and zeros. Back when I was an undergrad, we had, I think it was data communications, where we had to learn bits and bytes and calculate IP addresses. And I think it was assembly language programming. I don't think you all learned that anymore. But we had to take bits, turn them into bytes, turn them into assembly code. We're going to see IPv6 addresses are 128 bits long. And we have IPv6 addresses because with all the devices now connected to the internet, we've run out of IPv4 addresses. Excuse me. So a 32-bit address looks like this, a series of ones and zeros. Neither you nor I can remember this, read it, or write it. Computer can, however, but we can't. So we turn it into what we know as an IP address. Here's the function to convert binary to decimal in Excel. But I'm not going to ask you to do this, I don't believe. So this is our 32-bit IP addresses. We cut it into 4 8-bit segments. Then we turn the segment into decimal. So 10101101 is 173 and so on. That's how we get 173.22.194.171. Again, I don't think I'm going to ask you to calculate this. So again, we want our route to be shortest distance. So if we want to get to our host on router C and we're hitting router A first, which way do you think we go? Do we go A, B, C host, or do we go A, D, E, F, C host? Here we're going to go A, B, C. We want the shortest path. It's going to have the least cost for us, the most feasible. And we're looking at the same thing with transport and internet process. Again, this is all what HTTP does. So when you're typing that into your browser, you don't really need to anymore. But realize it's that hypertext transfer protocol that's letting IP addresses route from routing table to routing table. So we have a client, we hop to router 1. Hop 2, the internet process on router 1 talks to the internet process on router 2. So we got our message. Router 1 goes, hey, router 2, I need to come to you. How do I get there? You got hop 2. Router 2 goes to router 3. How do I get to you, bro? Hop 3. And same thing going to the server. DHCP is the process of how a device automatically gets assigned an IP address. The other way we can give an IP address is by defining it on the device itself. We really can't do that on Internet of Things devices like your smartwatches, etc. So we're starting up our Apple Watch first time. We reach out to our carrier once we connect to our Wi-Fi and say, hey, my device isn't syncing with my messages and mail. I need help. Oh, watch, you need an IP address. So your home router will give you the IP address, send it back to your phone. Your watch accepts it. Oh, I'm now 128.171.17.13. Great. Let me go to the internet. And you do the same way when you're at Marist with your laptops or your other hosts. Once you connect to Wi-Fi, you're dynamically given an address, and then you have internet access. DHCP will also define to you, if it's defined in its protocol, your DNSs, which is again how we get IP address to host name, as well as your gateway. And your gateway address is simply the address of your router. And your device needs all three to be able to get to the internet. You need all three because the internet needs to know who you are, that's your IP address. Your device needs to know, how do I turn a name, which is easy for my owner to use, into a number I can use. And it needs a gateway because that's how the rest of the internet's going to know where you are. We've talked about DNS already. Data links are the physical medium that connect networks. We see in the diagram here, we have a point-to-point network connected probably through fiber optics between two routers, probably in one location. Okay. Where we have a router then connect to 3 Ethernet switches. This is the foundation of an Ethernet switch network, where due to cable length limitations, we need more diverse numbers of switches. So we have 3 switches. Switches are where we connect host access points through RJ45 jacks. And lastly, we have a wireless segment of our network that's probably connected through wireless access points and wireless routers. I'm not going to go into great detail with these diagrams. It's just simply showing that we have some physical standard, copper, which is Cat5, Cat6, Cat7, or optical fiber, connecting to routers that sends frames back and forth, or packets back and forth, or segments back and forth. Same thing we're seeing here. So, list the physical links on the data link between A and X. So A is here, our host X is here. So we have to go physical link 1 to Ethernet switch 1 to physical link 5 to our host. Now we go Y and B. So we start at our client Y, we connect to our switch, we connect to another switch, we connect to another switch, and we connect to our host. So what does that tell us? This is all in the same Ethernet switch network, and we don't have to go out to the internet. If we did, the route would need a router. So the first example, a host is on one network and it needs to get to a host somewhere else. There's a picture of our switch, and yes, it goes in the same type of rack as our servers did. Under the gentleman's hands, you see 2 wire management racks. They're about 5U in size, and they help us pass Cat6 cable from one side of the rack to another to make things neat and tidy. So in this diagram, we're showing packets are carried inside frames in single networks. So in this diagram, our goal is to send a packet from host A to host B. We have an Ethernet network connected to this router, meaning this host is connected to a switch that is connected to a router. Host B is using Wi-Fi connected to a wireless access point. So two different mediums, two different networks to pass data along. So host A sends its frame to router 1, and ultimately we do this. We encapsulate it in the packet for a frame X, and then the frame gets sent to router 1. That's this process here. And again, our author will go into much more detail than I will. Then router 1 decapsulates it from the packet and re-encapsulates it for Y. So we went from Ethernet, that's the encapsulation part. So we made it Ethernet. We take the Ethernet out and we turn it into Wi-Fi. And once it's in Wi-Fi, we can now deliver it. We're going to finish up for this week with routers, access points, and corporate access points. And I want to ask another question while we're here. Let me get the good old textbook out. I would like to know just look at question 27 on page 33. Just A and C. Compare internet core routers with home routers and compare corporate access points and internet access points for consumers. Okay, so 2 questions for our lecture as well as our Lab Sim 0 and 1. So our core router is huge. It's usually the size of about 5 or 6 U, so almost 8 or 9 inches. All it does is route traffic, meant for high volume traffic, complex routing, remotely manageable routing tables to get traffic from A to B to C to D and back again. Whereas our home setup is a bit different. We have, say, our ISP of Spectrum, cable company here in New York, gives us a modem, which is where we get coaxial coming into our house, plugged into a device. We turn it into a wireless router, and then that router will deliver our Wi-Fi to our home. Okay. This broadband modem will be the point for our DHCP. It'll have our firewall, and it'll have our DNS server. Whereas our core router has none of that. It just routes traffic. So to do the same with a corporate network, we need wireless access points, which look similar to this. They're usually hanging in ceilings. They may or may not have antennas coming out of them. We also need Ethernet switches to connect clients to if they're not Wi-Fi. And we'll connect, like I said, we'll connect those switches to the router via fiber optic cables. Corporate access points are truly access points. They take your SSID, your network name, and your IP address range and broadcast it to clients connected to it. We remotely manage them, and we can have them work together. Large spaces may need 1 or 2 or 3 access points. In fact, Greystone has a large group home in Armenia, New York. It's about 40 minutes northeast of Poughkeepsie that requires 3 access points connected to a separate corporate firewall, which also acts as a wireless device connected to our home router. And that's it for this week, guys. So remember, watch your video, read your text, answer a couple lecture questions, do your lab sims, and start thinking about your group projects. Hope you guys have a great week. And again, welcome back to campus.